So here is our first video for the year. We're going to talk today about continuity and limits. Hopefully everyone was able to view the video, which if you're looking at this, I guess you are. They'll be posted on my website with the link, and they'll be available on YouTube so that you can go back and look at them anytime you want, should you want to use that for studying, or if there's something you want to go back and look at a little bit later throughout the year. So here we go. We're going to talk about continuity and limits. So the first thing we're going to talk about is what's called a limit. And as we're talking about a limit, we are going to talk about this notation that's over here. And this notation that's over here says that the limit as x approaches c. So x is approaching c. So if I look over here at the graph, I have x1 and x2. So x1 and x2, they're getting bigger and bigger, so they get closer to c. And on the other side, as x approaches from the left, x is going to go from x4 to x3. So it's getting smaller and smaller until our x value is actually c. And when my x value is c, if I follow that up onto my graph, and notice that this is f of x, my line is f of x. If I look at this, I can look at L. And so as x approaches c, my f of x becomes L. So that means my y value is L. L is the same thing as what my limit is. So that's basically telling me that, and we'll talk a little bit more about this much later in the year, I can take my x value, and my x value will become L, whatever I would substitute that value in at that point in time in my graph. So I'm also going to talk about, and we'll come back to that limit in a little bit. I know that that's kind of confusing. I'm throwing it at you, and now we're going to talk about discontinuity. We've talked about discontinuity a little bit in the past. There are a couple different types of discontinuity. One kind of discontinuity is called an infinite discontinuity. You'll have an infinite discontinuity when, if I look at this value of c, which is right here, if I look at that, one side of the graph coming from the right side of the graph, it's going up to positive infinity. As I look down and look at the graph, it's also going down as it's coming from the left, it's going to negative infinity. So since positive infinity and negative infinity are two different things, that means the graph is not continuous, because in order for it to be continuous, it would need to flow together and sort of match each other. So they'd have to go to the same spot. So since positive infinity and negative infinity are two different things, that means that it's discontinuous. I could also have what's called a jump discontinuity. A jump discontinuity means that the graph is not continuous here either, because if I look as f of x comes from the left, it approaches this number down here in the negative quadrant, and if I look as x approaches as it approaches from the right-hand side, I can see that it's going to be up here in the positive quadrant. So since those two numbers are not the same thing, that means that it is called a jump discontinuity, because in order to get from one part of the graph to the other part of the graph, I'd have to jump to get there. And the last part of the discontinuity is called a removable discontinuity. A removable discontinuity means that my graph is pretty much solid, which means that it's continuous, except, oh, look at that, I have that little hole there. That little hole there tells me that I can't have that part of the graph, because that would give me most likely a 0 in the denominator of my particular function of my fraction. So since I have that hole there, that tells me that it's going to be a removable discontinuity. And I could find a way to sort of get rid of it if there were some way that I could. And I'll show you examples of all three of those. But those are the main three types of discontinuities. So in order to find out if something is continuous or discontinuous, I have to first verify that f of x is defined at c. So that means it exists. That means I can't have a 0 in the denominator of a fraction, basically. Then the second test that I have to do is I have to make sure that f of x approaches the same number from the left and from the right. So that's telling me that the limit of f of x has to exist. So as I look from the left and look from the right on the graph, they have to approach the same number. And then the value of f of x approaches from each side is f of c. In other words, if I plug c in for x, I will get f of c. So we'll talk about all of those three things in just a second. So here's my first problem. I have f of x equals 1 over 2x plus 1, and I want to verify that it's continuous at the point 1/2. So the first thing I have to do is I have to find out, does f of 1/2 exist? So I'm going to plug 1/2 into the function. If I plug 1/2 into the function, then that means I would have 1 over 2 times a half. 2 times a half is just going to be 1. So 1 plus 1 is 2. So that means it equals 1/2, which is what we have here. And that tells me that it is defined. So part 1 of my test for discontinuity or continuity applies. Then I look at the second thing. Does the limit exist? So what I do is I construct a table. And 0.5 is the number that I'm concerned about. But a limit we want to look at as it comes from the right and as it comes from the left. So I'm going to put in numbers. Notice how I have, when the numbers are bigger, I put 0.001, 0.01, and 0.1. And I look and I plug those values in for x into my function. And when I plug them into my function, I get these numbers down here from f of x. And then I do the same thing coming from the left. So there's my numbers. And again, I have 0.49, 0.499, and 0.4999. And I plug those values in. And then I want to see, what do I think happens at 0.5? Do those numbers look like they're kind of in between? Well, look at these two numbers are the numbers that we're going to look at. I'm going to look at that number there and that number there, 0.5001 and 0.5000. They're relatively close. So that tells me that I could pretty much assume that 0.5 is going to be in between what those two values are. So that tells me that it's getting closer and closer to a half. So our number of our f of x as x approaches 1/2 is 1/2, which we found from the last slide, pretty much applies. So that tells me that the limit does exist. And then the last thing I have to do is I have to make sure that it is actually equals a half. So if I look at my graph, here's my graph of that function. At f of 1/2, I happen to get 1/2. So that tells me that it is continuous. Now, if you look at the graph, you'll notice that it is continuous at the point 1/2. But then if I look over here at negative 1/2, that tells me over there I probably have a discontinuity. And that discontinuity would be an infinite discontinuity. But we're not worried about that one at negative 1/2. We're only talking about positive 1/2, which tells us it is continuous. So here's another example. I have the equation f of x equals 1 over x minus 1. I want to know if it's continuous at 1. So the first thing I'm going to do is I'm going to stick 1 in for x. But when I stick 1 in for x, I get 1 over 0. 1 over 0 tells me that it's undefined. So that means it does not exist. So that tells me that it is discontinuous. But I need to figure out what kind of discontinuity. Well, now I'm going to look here. And I'm going to look at my table. And if I look at my table, coming from the right and coming from the left, you'll notice that coming from the left, I have negative 1,000. And coming from the right, I have positive 1,000. So since one number is going up and the other number is going down, that's pretty much hopefully going to give you a hint of what kind of discontinuity it's going to have. So if I look at the next slide, I will see that I have a discontinuity, and there's my particular graph. And if I look as if it's going up on the right and down on the left, that basically tells me that I have an infinite discontinuity. And here's the last one. I have a function here. And if I look, I'm going to put the 2 in for x. If I put the 2 in for x, I get 0 over 0. 0 over 0 is a special type of case. And we'll talk again a little bit more about that in our last unit of the year. But 0 over 0 tells me that we have something going on there. So now I'm going to make my table. And if I make my table, you'll notice that at 2, I have something at 1.999, which is 0.25. And if I have 2.001, I also have 0.25. So that tells me that 0.25 seems to be my limit. And then if I look over here, you'll notice that it's going to have what's called a removable discontinuity. Because if I look at 2, there's no discontinuity there. It's not a jump discontinuity, and it's not an infinite discontinuity. So we already established that it was a discontinuity, so that's what's called a removable discontinuity. And you should notice that if I factor the denominator, and if I have x minus 2, and then I have x plus 2 and x minus 2 in the denominator, you should be able to cancel those out, the x minus 2. So at 2, it is a removable discontinuity because I can cancel it out. It can be removed by factoring and simplifying the fraction. The last thing we're going to talk about is what's called the intermediate value theorem. And we did talk about the intermediate value theorem last year at some point. I'm not exactly sure when, but at some point in time we did. And the intermediate value theorem tells me if I have a continuous function and at some point I have a value that is negative, and if I have some point that I have a value that's positive, that tells me somewhere in between those two on the interval between the x values, which in this case was a and b, then at some point it must have been 0. So that pretty much tells you if the y value is positive and another y value is negative, somewhere in between there is a 0 value. So we want to figure out where our zeros would occur in between the point -2 and +2. So I'm going to make a table between -2 and +2. Notice that I have in my table my y values. I have a positive number here and a negative number there. So if it goes from positive to negative, that tells me there must be a 0 in between -1 and 0. And then over here, I have another negative and a positive. So since it's in between a negative and a positive, somewhere along the line there has to be another 0. So that means there will be another 0 in between -1 and 0 and 1 and 2. And that's pretty much what we can find. If I look in between here, -1 and 0, there's a 0 right there. And if I look between 1 and 2, there's a 0 right there. And that's what the intermediate value theorem says for us. So there you have it. Hopefully it wasn't too long, and hopefully you can understand what we're talking about. And you now need to go through the Google document and go ahead and do exactly what they say and answer the couple questions. And then we'll come back and talk more about this when I see you in class the next time. Thanks. Good night.